Dr. Suzie Husain specializes in regenerative agronomy, soil diagnostics, and sustainable agriculture systems. With over 15 years of experience, she leads regional initiatives to improve soil governance, train practitioners, and develop certification frameworks that restore soil integrity within farming landscapes across the global South, ensuring food security and helping communities and nations resist climate change impacts.
Today I want to speak about something that physically beneath us but strategically above many of global risks that we are discussing right now, which is the soil. So usually when people talk about the soil, they think about the farming, fertilizers, right, crop yield, and even on the land productivity. So I think this is not wrong, but it is incomplete. So today's I will cover on the hidden infrastructure on how the soil regulates water, carbon, and global pollution risks in the tropics. So for the convergent risk, right, a crisis. So we are now living in a period with multiple environmental crises that are converging. So the climate extreme are no longer a future projections because they are already changing the rainfall density, drought durations, heat stress, and even the flood frequency and the stability of water system. So, but here is the problem, right? So most of our response is still sectoral, which means that when the floods happen, we say it is a drainage problem. When drought happen, we say it is a water supply problem. And when the water is polluted, we say it is a sanitation or waste management problem. For example, when the crop yield declines, so we say it is as a fertilizer problem. But in many landscapes, especially tropical landscapes, right, these are not separate problems. Actually, they are connected through the soil functions. So the soil is a control layer between atmosphere, vegetation, water, carbon, and even on the human activities. So when that control layer weakens, so the whole system becomes unstable. So this is a very critical point when a degraded soil cannot regulate a disturbed climate. So the first step is to recognize what is missing in the most climate and sustainability discussion, which is that soil as an infrastructure. So the missing infrastructure, this slide will show you, ladies and gentlemen, on the central idea of my presentation, which is that you can see that the soil perform a distinct public functions. I call them as biospheric infrastructure services. First, you can see that it is hydrological infrastructure, right? So where it absorbs, store, filters, and also slowly release the water. And then the second, it is a carbon infrastructure, which is that it stores the carbon, but more important, it uses carbon to build the structure, microbial activity, and biological resilience. And the third is that pollution buffering infrastructure. Pollution buffering infrastructure, which is that soil can retain, filter, transform, and also or slow the movement of contaminants. So, and the last one, on the fourth, it is the biological infrastructure, which it supports the roots, microbes, nutrient cycling, and ecosystem recovery. So, I think this is why the soil should be not treated as an inert substrate, and soil is just not only a material, soil is a functioning system. And when that system fails, the cost is not only borne by farmers, right? It is borne by water utilities, by the government, communities, food system, and climate risk managers. So soil is the control interface between atmosphere, water, biology, and human survival. So now let us look at why this issue is particularly critical in the tropics. So, we know that these tropical soils operate under very intense pressure. So, we have a high rainfall, high density of rainfall. That means that more leaching, more runoff, more erosion, and higher risk of sediment movement. So, we have a high temperature, which is that can accelerates the organic matter decomposition. So, carbon can disappear very quickly, and if biomass is not continuously returned to the soil. So I can say that many tropical soil are highly acidic, and this acidic system, aluminum toxicity can restrict the root growth and reduce the nutrient uptake and limit the rooting depth. So the root system is shallow and the soils become less able to access water and nutrients during the stress. So we also have intense weathering, which means that many tropical soil are old, highly leached, and naturally low in some nutrient reserve. So this means that tropical soil can be powerful regulators, but they are also highly vulnerable. So which means that the key is not whether a tropical soil is good or bad. The key is whether it remains inside its operating window. So when the system cross a threshold, so for example on the structure will be collapsed, the organic matter will start declining and the root will start to restricted, and at some condition we can see that the compaction biological become more weakens. So I think the landscape can shift very quickly from regulation to failure. So the first visible failure is usually water. So let us have a look at what happens when the soil buffer fails. So in this slide, this is one of the most important slides when the rainfall hits a healthy soil. So part of it infiltrate, right? So it moves through pores, it is stored in the root zone, and it supports the plants, microbes, groundwater recharge, right? And also the slow water release. So, but when the rainfall hits degraded, right? Degraded soil. So the behavior start to change, which is that compacted soil have fewer connected pores. Bare soil has poor surface protection. Low organic matter means a weaker aggregation, and poor the root growth mean fewer biological channels. So rainfall does not enter the system. So it moves across the surface and it becomes runoff, erosion, sediment, nutrient loss, and even on the flood risk. So I think this is why I always says flooding is not only a rainfall problem. It is often an infiltration failure. So if the soil cannot receive the water and the landscape has no buffer, so for the farmers, this means that yield become more instability. So for rivers, this means that sediments and contamination. And for government, this means infrastructure pressure. And then to understand this properly, we need to stop seeing soil as a substrate and we start seeing soil as architecture. So soil is architecture. What it means, right? So the most important part of the soil are often not the solid particle. They are also have a spaces between the particles. For example, macro pores, for example, it allow on the water movement, drainage, aeration, and root penetration, right? And micro pores will hold the water. So the aggregate will protect the organic matter and create a stable structure, and the roots and microbe act like as a biological engineers. So when we destroy this architecture through compaction, erosion, over tillage, poor cover or poor organic matter management, so we do not simply lose the soil particle actually. Actually, we are losing the lose on the function. So that's why when we are talking about the soil health, for example, it refer on the capacity of the soil to reach as a living system. Right, so this is why, for example, that we can see that two soil with a similar laboratory nutrients value can behave completely differently in the field. Right, one soil may be absorb rainfall and support the deep root, but the others may seal on the compact and also generate the runoff. So I think the field performance is not explained by chemistry alone. So it is must be explained together by the chemistry, structure, biology, roots, and landscape position together. And one of the strongest drivers connecting all these function is carbon. All right. So carbon that works, which means that when people hear about the soil carbon, they are often thinking about the climate mitigation. That is important, but I think this is not enough. Why? Because soil carbon is not only stored in carbon, actually it is a working carbon, which means that the carbon feed the microbial communities. It help form the aggregates, improve the water retention, buffers the temperature, support the nutrient cycling, and make the soil less fragile under stress, which is an example that El Nino that is coming right now, right? So in other words, the soil carbon is a functional infrastructure. So in tropical system, this is especially important because heat and moisture will accelerate the decomposition. So if biomass return is low, right? So if soil are exposed, or if a disturbance is too frequent, so carbon will decline very quickly. So we cannot discuss the soil carbon only as a number of carbon markers. We must also ask, what is that carbon doing? Is it improving the aggregates, supporting microbial function, stabilizing water behavior, and reducing erosion and also the runoff? So carbon in soil just not only a climate asset, it is the currency of resilience. So but whether the carbon is stored or lost, it depends strongly on moisture, right? So that brings us to the soil moisture bath. Okay, on the moisture valve, if you can say that we know that the soil is a control valve, right? So if the soil too dry, so microbial activity will slow down and plant growth start to declining and carbon input start to decreases, right? So if the soil is too wet or waterlogged, so oxygen become limited. So that change the microbial pathway that can increase greenhouse gas emission, especially methane and nitrous oxide in certain condition. So between these extremes is the functional zone, right? For example, on the enough moisture for biological activities, but enough oxygen for healthy root and microbial processes. This is why the soil structure matters so much, right? So good structure will give both on the soil, on the water, and also on the air, right? And the poor structure give us an extreme. For example, stress during the dry periods and waterlogging during the wet periods. So in tropical landscape, the problem is not only lack of water, right? So it is also poor on the regulations of water. And the living system that manage much of this regulation we call is as a soil biology. So that's why in this slide, I will talking about the invisible workforce, which is the biological operating system. So we know that the soil microbe just not only decorative biology, right? So they are on the biochemical operating system of the landscape, right? So they are, for example, what the roles they can do is they can mineralize the nutrients, they transform organic matter, support on the aggregate, interact with the roots, regulate on the disease suppression, and also influence on carbon stabilization. So also a soil that can have a fertilizer but still biologically weak. So I think this is a major misunderstanding in many agriculture system, which is that chemical fertility can support the plant growth in the short term, but biological function determine on the resilience, recovery, nutrient efficiency, and long-term soil performance. So for example, in my field experience, right, many degraded soil not only fail because only we are missing one nutrient, right? So usually they are fail because the soil system has lost coordination. For example, the weak roots, low carbon, poor aggregation, and even the low microbial activity. So I think this is why the soil health must be diagnosed as a living system, not a single laboratory value. So now let us connect on the soil function to the theme of this webinar on the water, sanitation, and pollution. All right. So the soil can act as a filter, right? But only at up to a point, which means that when the soil is healthy, it can slow water movement, it can retain the sediments, absorb on the some contaminants, and retain on and also support on the microbial degradation of certain compounds. But when soil is degraded, right, so it become a conveyor. So which means that the soil, the sediments that move, nitrate move, phosphorus that attach to eroded particles, pesticide residue can move with runoff or leaching or pathogen from the waste or livestock system, or poor sanitation can move through a water pathway. I think this is why many pollution problems are actually a pathway problems, right? So we often focus on the pollutants, but actually not enough on the transport mechanism, which is that the nutrient become a water quality problem when the landscape allow it to move, right? So a pathogen become public health risk when the soil and water pathway are poorly managed. Another example is like a pesticide, for example, right? So it becomes a downstream risk when the soil buffering is weak and runoff is high. So pollution is not only about what is applied to the line, right? So it is about whether the soil can regulate movement through the landscape, right? So I think this leads us to a major contradiction in agriculture and sustainability. All right. So I think we know that agriculture is essential for food security, right? So, but agriculture is one of the major interfaces where the water, nutrients, and sediment, and even on the pollution risks meet, right? So this is the agriculture contradiction. So we need a productive land, but if the productivity is achieved by degrading soil structure or exposing or bare land, overloading with the nutrients, or weakening on the biological function, so we create the hidden cost, and this cost usually will be bear with our farmers, which is that translate that later will appear as the water pollution, runoff, greenhouse gas emission, lower fertilizer efficiency, and definitely on the unstable yield. So I think this is why I believe that the future of agriculture cannot based only on the input efficiency. It must be based on the soil function efficiency, which means that how much the rainfall when enters to the soil, and how much nutrient can be retained and used, and how much the carbon is protected, right? So I think this is the next level of agronomy, which means that just not only how much yield that we did get, but actually what the system cost did we create and get that yield, right? So when this failure accumulated, so we get on the cascading failure, right? So I think this is the example on the chain reaction that usually start very quietly, right? So for example, there is a land cover change, there is a compaction layer, so we can see a decline in organic matter, a reduction root depth, right? And then on the weaker microbial system. So at first, it may we cannot absorb it, or maybe it not look too dramatic, but then rainfall comes, heat comes, right? The drought comes, so more fertilizer has been added, so much more runoff happen, and more sediment move, so eventually the landscapes loses the regulation. So I think this is what I mean by cascading failure, which means that soil degradation is rarely a one isolated problem. So actually this is a system sequence. So and because the soil is below the ground, so the early warning are often missed or overlooked, right? So by the time the symptom become visible above the ground or the canopy, for example, so the functional damage may already be advanced. I think this is why the soil health is just not only a technical issue, it is a governance issue. So on the failure of governance, we misprice the land risk because we misunderstand on the soil function. So in many policies and markets, right? So the soil is treated as a private land, a farm substrate, or a production space. But the soil perform public functions, which means that it regulates water, reduce sediments, buffer the pollution, even store the carbons. So if the soil perform public function, right? So then the soil degradation become a public cost. So those costs may appear as a flood damage, water treatment costs, reservoir sanitation, food insecurity, or even the rural poverty. So this is why the soil health must move from the farm management into infrastructure governance, which means that we need the soil indicators in water policy, we need soil function in ESG reporting, we need a soil risk in climate adaptation, and also we need a soil diagnostic in land use planning, right? So if a soil is a public regulator, then soil health cannot remain only a private farm responsibility. So how we want to move from awareness to decision intelligence? This is where the functional diagnosis matters. So this is where the shift framework comes in, right? So on the decision intelligence that require functional diagnosis. The problem with many soil assessment is that they stop at numbers, right? Numbers, pH, organic carbon, nutrient texture, and other lab values that are important. But numbers alone do not tell us the full functional of the soil. So the question is not only what is the soil value actually. So the better question is, what does this value mean for the root growth, water movement, nutrient efficiency, biological activities, carbon stability, or even on the landscape risk. Right? So the SHE framework translates the soil science into the functional diagnosis, which means that it looks at chemical condition, physical structure, biological activities, root zone performance, and landscape context. So then it connects those findings to management, governance, and risk decision. And this matters because different soil can require different interventions. So some maybe need acidity correction, structure recovery, organic rebuilding, or even on the erosion control. So a good soil health system just does not give a generic recommendation. It diagnoses on the limiting function, right? So let me close with the main message of this presentation. And one thing before I end to the on the end the slide, right? So usually on the SHE framework, what we did is we did categorize our soil to three level: S3, S2, and S1. And from this conversion, usually we convert into from S3, which is the degraded soil, to S1, which is the regenerated soil. All right. So I think on this the main message on this presentation, we need to understand that the soil is just not only where we plants grow, right? So it just not only the support the crops or just not only receive the fertilizers. It is a living infrastructure that regulates water, store the carbons, filters the pollution, support biology, and even determine whether the landscape remain resilient or already collapsed, right? So for tropical landscape, this is not just only a theoretical, it is immediate, which means that rainfall is becoming more intense now, heat is start increasing, land degradation already spreading, and even on the water quality is already under pressure, right? So agriculture is asked to produce more with fewer ecological buffers. So we need a different way of thinking, right? Just not only treat the soil as a background, not treat the soil health as only fertility, right? Just do not treat the soil degradation as only the farmers' issues, right? So we need to treat the soil as biosphere infrastructure. We diagnose the function, manage the risk, and also protect the biospheres, right? So I think that's all from me. Thank you very much, and I look forward on to the discussion.